So, what we're going to be talking about for the next probably several weeks is different aspects and different types of chemical bonds. Okay, so everything we're going to talk about this week is called ionic bonding, and then we'll go to something called covalent bonding, and then how those bonds form molecules and what the shapes of the molecules are. So, over all of that is this one picture, which is that atoms form bonds by either sharing or transferring electrons back and forth. So sometimes, which is what we're going to talk about today, atoms actually give away electrons and other atoms take them. So there's a complete transfer from one atom to the other. That's what we're going to focus on first. And then later, we'll talk about, well, what happens when the electrons aren't given away or taken, but actually shared and moved back and forth and spend some time around both atoms. That's a different kind of bond that we'll get to later. So to start with, so that again, that first slide talks about the whole unit that we're going to go through in the next several weeks. More specifically, starting today, we're going to be talking about something called ionic bonds and ionic compounds. Those bonds come from the fact that sometimes you have positive ions and sometimes you have negative ions, and positive and negative attract each other. So if you get a bunch of ions together, the positive and negative are going to latch onto each other like magnets. And that's how we get ionic compounds like table salt, or the salt that you put out like this morning when the driveway is icy or the sidewalk's icy. It's an ionic compound formed by positive and negative particles that are latched onto each other because of that opposite electrostatic charge. In general, a chemical bond is any force holding two atoms together. Okay, and it comes from the fact that you have the positive protons in the nucleus of one atom pulling on the negative electrons of another atom, and that creates this force holding atoms together to create compounds and molecules or ionic bonds in ionic compounds. They're all chemical bonds come down to this interaction between positive and negative. When we talk about compounds and bonds and chemical reactions, all chemical reactions come back to this one fact. Every atom on the periodic table wants 8 valence electrons. That is the ideal number. That is the most stable number you can have. Unfortunately, most atoms don't come that way. They're not made with 8 valence electrons. They're made with either too many or too few. And then they have to adjust by either giving away or taking or sharing electrons in order to achieve that 8 valence electron configuration, which is the best one as far as atoms are concerned. When you gain or lose electrons, that's when you get ions. And we've talked about ions a little bit, a couple of times. We talked about it when we first did the atomic structure. There's ions and isotopes of different electrons or different neutrons. And I mentioned it a little bit in the periodic table because depending on the group number, different elements tend to form different types of ions. So we're going to spend a little more time on that now and use that to form compounds and formulas, and then later on sharing electrons creates molecules. Remember, an ion is an atom with a positive or negative charge. And it gets that positive or negative charge because the number of electrons has changed. It's either gained extra electrons or it's lost some of its electrons, and that creates an imbalance between the positive and negative. So if you lose one or more electrons, but starting with one, once you start losing electrons, you turn into a positive ion, which might sound backwards. You're losing something. How does it become positive? You have to remember that the thing you're losing is a negative thing. So lithium, for example, has 3 electrons and 3 protons. That's its normal Sort of that's how it's made. The 3 protons and the 3 electrons cancel each other out and create a neutral atom. Positive and negative are equal. And all atoms start out this way with no charge because the protons and electrons are the same. We talked about that with the structure of the atom. But if lithium loses one of its electrons, it has 2 electrons left, but it still has 3 protons because those protons don't change ever. So the fact that it went from 3 and 3, which, if you add it up, comes out to 0, no charge. Now you add -2 and +3, and you end up with +1. So that lithium atom is now a lithium ion with a positive charge. And the way I always remember it is, losing an electron, you're taking away a negative, you're subtracting a negative, which creates a positive. So just thinking about it in terms of the math that way, it helps me think about it. In terms of how you can figure out whether you're going to end up with a positive or negative ion, even without knowing how many electrons it might have or how many it might lose. All of the metal elements, which is the ones on the left, right? The first 2 columns, all the columns in the middle part, and then even some of the ones on the right-hand side, those are all the metals. They lose electrons. That's just the way it works. So if you see an element that's from that area of the periodic table and you're trying to figure out what kind of ion it's going to be, if you know nothing else, assume it will be a positive ion. You'll be right. I can't think of an exception to that rule. Figuring out the actual number of the charge takes a little more work, but just knowing that the metals are the positive ones, they're on the left-hand side of the periodic table, that will get you, a good part of the way there. Then, if you think about adding electrons for an element, something like fluorine, fluorine starts out with 9 electrons and 9 protons. If it adds an electron, if it gains an electron, and I say loses and I say gains, this is actually electrons that are being moved from one atom to another. So this lithium lost an electron, this one gains an electron, that could be a transfer from lithium to fluorine. These electrons don't just appear out of nowhere. They come from different atoms and go to different atoms. If you add an electron to a fluorine atom, now you have 10 electrons and still 9 protons. That gives you a negative charge because the negative outnumbers the positive by 1. So that creates a negative ion, which is what the non-metal elements do. Okay, so metals on the left-hand side of the periodic table are going to be positive ions. Non-metals in that upper right-hand corner are going to be negative ions. And remember, I said that all of this is driven by the fact that atoms want 8 valence electrons. Well, it turns out that the noble gases all have 8 valence electrons. So all the atoms on the periodic table, which I'm going to show you in a minute, they're all trying to be like the noble gases because they're the most stable elements on the table. So they'll move by gaining or losing electrons in terms of the number of electrons until they get to one of the noble gases or the configuration of one of the noble gases. And what determines whether they add electrons or lose electrons is kind of what's the shorter path to get to a noble gas. All right, this last column, group number 18, these are the noble gases. And we call them noble gases because they don't react with the other elements on the periodic table. They stay to themselves. That's where the noble part comes from. They only stay to themselves. Well, the reason they don't interact with other elements is that they all already have 8 valence electrons, which is what every element wants. except helium, which has 2. Still a noble gas, it's still a complete set, but because it's in the first row, it only has 2 electrons. But the rest of the noble gases have 8, which is the ideal number. It's like I've got 24 crayons in the box. I don't need anything. I don't have anything extra. So if the whole driving force between interactions of atoms is this desire to have 8 electrons, they don't do it because they already have 8 electrons. They don't need to interact. But every other element on the whole periodic table don't have 8 valence electrons. So all of these other elements want what the noble gases have. Okay, the noble gases are the celebrities of the periodic table. Everybody wants to be like that. And they will do essentially anything to get there. In order to get to the 8, which is the noble gases, these other elements either have to move up or down the table, right? If you start over here at sodium, right? Sodium is in between argon as a noble gas, and then if I kind of go back around the other way, neon is a noble gas. It's between number 10 and number 18. Those are the 2 noble gases closest to sodium. Well, in order to get to argon, sodium would have to add 7 electrons to get up to 18. In order to get to neon, sodium just has to get rid of one of its electrons to get down to 10. And as you might imagine just from the sheer number, it is easier for sodium to give away 1 electron and move down than it is to add 7 electrons and get up to 18. Because what you have to remember is in order to get those 17 electrons, or 7 electrons to get to 18 rather, it has to get them from other atoms. So sodium would need to go out and take 7 more electrons from other atoms in order to get up to 18. That's not easy to do. What is easy is just giving away 1 of its electrons to somebody else who wants it. And then it drops down and it goes from 11 electrons and 11 protons down to 10 electrons and still 11 protons. So it becomes a positive 1 ion. And as far as the electrons go, it now looks like neon, which is a noble gas, which is what all the elements want. It's still sodium because it still has the protons. But as far as its electrons look, if you just looked at the electrons from the outside, it looks like neon. So it has changed its appearance to become like a noble gas. On the other hand, if you had, I mentioned fluorine, right? Fluorine is here. Well, fluorine is in between helium and neon. So it's number 9. So it can move up 1 step to get to neon, or get rid of 7 electrons and get down to number 2 helium. In this case, it's easier for fluorine to move up 1 spot. So fluorine goes from 9 electrons and 9 protons to 10 electrons and 9 protons, which makes it negatively charged with a charge of -1 because it gained 1 electron. All right. So just to show you a couple more examples, and I want to show you one last thing. So again, just to show you a couple more examples and another way of looking at it, or another way to kind of figure it out. When we talked about the valence electrons, electron configuration in the periodic table, and the group numbers tell you how many electrons they have, valence electrons. Well, the elements that have less than 4 are going to form positive ions. They're all the metals anyway. But it means they have either 3, 2, or 1 valence electrons, so it's easier for them to give away electrons than it is for them to add up to 8. So all those elements, like calcium, which starts out with 20 electrons and 20 protons. So it's here. So it's in between krypton and argon. Well, it's a lot closer to argon than krypton in terms of where it is on the periodic table. So it's going to go down to 18 by giving away 2 of its electrons. Okay, so it goes from 20 electrons down to 18. So this one gives away 2. The other ones we showed gave away or accepted 1. But it still has the 20 protons, which leads to a charge overall of +2. Okay, so the number is equal to how many electrons were either gained or lost. It lost 2, it's got a charge of 2, and since it went down electrons, it's a positive charge. And then chlorine, which is here, is between neon and argon. But it's a lot closer to argon than neon, so it's easier to go up 1 spot than down 7, which means chlorine is going to tend to accept an electron and go from 17 to 18. 18 electrons and 17 protons, that's -1 total. So the chlorine ion is going to end up with a charge of -1. Now, if you were writing this, as an answer for something, when it's only a 1, you don't actually even need to include the number. You can just put the negative or positive sign. It tells me 1. But you always have to include the number when it's not 1. That's true of formulas when we get to that too. If it's just 1, you don't need to include the number. If it's more than 1, you do. Okay. So, I wanted to go back and just remind you of the periodic table and the valence electrons and how that affects the charges. So, I skipped over group 14. The elements in group 14, many of them just don't form ions. They do the sharing thing that we're going to talk about later. But I want to acknowledge that I didn't forget that. I'm skipping over it for a reason. So looking back at what we did with the periodic table, elements in group 1 have 1 valence electron, and they tend to form +1 ions. Group 2 has 2 valence electrons, and they form +2 ions. Over here, group 13 forms +3 ions because they have 3 valence electrons. And then when we get to 5 valence electrons, we've now crossed over to where it's shorter to go up than down. So now we start the negative ions with -3 because it's going to take 3 steps to get up there. And then we finally have -1. And then again, the noble gases aren't going to form ions because they don't need to. Now, there are some exceptions in here, a couple of them anyway. And I skipped over the middle part because a lot of those elements are kind of different in terms of many of them can actually form multiple types of ions, still positive, but different numbers. Like iron can sometimes be +2 or sometimes be +3. We'll talk about that later. But as a rule, I was trying to give you the rule, and there are exceptions, but if you use this setup, +1, +2, +3, and then over to -3, -2, -1, that will do it, 95% of the time, if not more, when you're trying to figure out the charges, and that will go into what we do with formulas and compounds.